So our third simple machine that we're going to talk about is a wheel and axle. So we've already covered lever and done IMA and AMA, as well as forces and distances in a lever. And we just finished inclined planes, where we saw that our IMA and our AMA are very similar to levers, but we just have to look at our length of our ramp and the vertical height of our ramp. So now we're looking at a wheel and axle. So here are the notes that you want to write down. That the wheel is a lever arm fixed to a shaft, which is called an axle. So you can see on the picture on the right where they're showing a lever. The fulcrum is now on one side of the lever, and you can see your effort and resistance forces. And we're going to talk about why the lever can be either a second or third class lever, depending on where our effort is being applied and where our resistance is being applied. So you can see the wheel and axle move together as a simple machine, but it's important to know within the wheel and axle system which is applying the effort and which is applying the resistance, the wheel or the axle, which we're going to talk about. So you want to write an example of an axle driving a wheel, which in the animation on the left you can see the wheel moving. That's like any wheel on your car, or a wheel on a wheelbarrow, or a wheel on a golf cart. Any wheel that is driving something, the axle is spinning and the wheel is spinning because of the axle. So in your car, when you apply gas to the gas pedal, it's spinning the axle, which is in turn spinning the wheel. So we normally think of a wheel and axle system where the effort is the axle and the resistance is the wheel. But now it's asking us, can you think of an example of a wheel driving an axle? So here are some examples. We have a steering wheel because you are actually the one turning the wheel, and the axle below is turning because of it. So you are applying effort to the wheel, and the resistance force is on the axle. To the right, you have a knob and a faucet, and both of those, you're spinning the wheel, and the axle below it is spinning because of the effort you're applying. So now you can see that our wheel and axle IMA equation is just dE over dr, which is the exact same equation that we used for levers, the effort distance over the resistance distance. So you can see on the little picture on the right, you can see that we have our wheel, and they give us some lengths. So that little symbol next to 20 inches and 6 inches just shows diameter. So it's saying the diameter of the wheel is 20 inches and the diameter of the axle in the middle is 6 inches. We know that our circumference is either 2 pi r or pi times diameter. So they're telling us that our effort distance is either the diameter or the radius of the effort, which is either the wheel or the axle, depending on if we have a steering wheel or a wheel on a car. The resistance distance is the same. So if we have our IMA formula as pi times our diameter, the pi's are going to cancel, and all we have is dE, which is our effort diameter, over dr, which is our resistance distance. Same way if we use our 2 pi r, those 2 pi's will cancel out. So the equation that we're left with, all this is showing you is that the dE over dr in a circle in that wheel is still going to be dE over dr. So if we want to know the IMA of this wheel, we can look at the axle and the wheel distance and try to figure out the IMA using our equation. So it's saying, what is the IMA if the axle is driving the wheel? So that means our axle is our effort and our wheel is our resistance. So that's going to say that our effort distance is the axle, which is 6 inches, will go on the top of our equation. Our resistance distance is 20 inches on the bottom, so we're going to have an IMA of 0.3 to 1, which is less than 1, which means we have it's going to do more force and less distance. What is the IMA of the wheel if the wheel is driving the axle? So now we're picturing the wheel to be a steering wheel. So now that means the wheel is our effort distance and the axle is our resistance. So our wheel is now going to be on the top, or 20 inches, and our resistance distance is our axle, which is 6 inches. So that's going to give us a mechanical advantage of 3.3. So that means less force that we have to apply and more distance. So now we want to see our AMA. And our AMA is going to be the exact same equation that we've seen for levers and inclined planes, which is FR over FE. So the AMA of the above situation, if the wheel is driving the axle, so if we're looking at it as a steering wheel situation, then the wheel is driving our axle, the wheel is our effort, and the axle is our resistance. So we want to put our resistance force, which is going to be that 200 pounds, over our effort force, which is the 70 pounds, and we're going to get 2.86 as our actual mechanical advantage. We can find our efficiency of it if the wheel is driving our axle. AMA is our 2.86, and 3.33 is what we got for the IMA on the previous slide. So that gives us an 86% efficiency. So now let's do some sample problems. So this is a problem that is in your packet, so make sure you follow along. We have this system attached to a wheelbarrow. So we want to find the IMA, and they're giving us the diameter of the wheel and the axle, and then the forces on those respective parts of our system. So our givens and unknowns, the first thing we need to do is figure out if the wheel is driving the axle or the axle driving the wheel. We can see from the fact that this is a wheelbarrow that the effort is going to be at the axle. We are pushing the wheelbarrow and the axle is spinning the wheel. So our effort distance is going to be the diameter of our axle, and our resistance distance is going to be the diameter of the wheel. So our equation that we're going to use is IMA is dE over dr. When we plug those in, we get 6 inches over 24 inches. So we have an IMA of less than 1, which is what you're going to see pretty much every time that you have a wheel and axle system where the axle is driving the wheel. Now we want to find the AMA of the system. So we still have our effort at the axle, so our effort force is going to be the force on the axle, which is 135. Our resistance force is going to be that force on the wheel, which is 20 pounds. Our AMA is force resistance over effort force, so we plug those in and we get our IMA of 0.148. Now to find the efficiency, we know we take our AMA and our IMA, which are our givens and unknowns, and we have our equation. Percent efficiency is AMA over IMA times 100. And when we plug that in, we get our 0.148 over 0.25, and this is only 59.2% efficient. Now, what if we have this system and the wheel and axle is used as a steering wheel? So we are actually turning the wheel, and the axle is turning because of it. So our givens and unknowns are going to tell us that the effort is now at the wheel. We are actually spinning the wheel. So the effort distance is going to be that 12 inches, which is the diameter of my wheel. And my resistance distance is only going to be 2 inches, which is my axle. My equation is still dE over dr. And when I plug them in, I'm going to get 12 inches over 2 inches, which is going to give me an IMA of 6. You're always going to see IMAs of greater than 1 whenever you have the wheel spinning the axle. Now what about our AMA? We have still the effort at the wheel, and our effort force is 20 pounds. Our resistance force is 100 pounds. Our equation is still force resistance over effort. So now we have 100 pounds over 20, and our IMA is going to come out to be 5. Now the efficiency of the system, all we have to do, got our AMA and our IMA of 5 and 6, plug it into our percent efficiency equation, and that 5 over 6 times 100 is going to give us an 83% efficiency. So now I want you to try those other sample problems on your own. If you have trouble, you can watch the second screencast. If you don't and you think you're good, then you don't need to watch that screencast. You can just call me over when you're done with your practice problems.